Hi everyone, welcome to my channel. My name is Said Ali Abbas and today we are going to discuss what are homogeneous differential equations. So this is our lecture number 5. In the last lecture we have studied what are separable differential equations and how to solve separable differential equations. So the purpose of this short course is to provide general and to the point information that is required for understanding differential equations. I'm not covering the details regarding differential equation. I'm just covering the basic, or you may say, relevant concepts regarding differential equations. So let's start. So what we are going to discuss today, the major highlights of today's lesson will be, first we are going to discuss what are homogeneous functions, and we are also going to see some examples related to homogeneous functions. It is important to understand the homogeneous functions first, and then we will move towards the homogeneous differential equation. So first task will be the understanding of homogeneous function and some examples related to it. Then we will see the definition of homogeneous differential equation, and we are also going to solve an example related to homogeneous differential equation that will cover that how we can solve a homogeneous differential equation. So let's start with the definition of a homogeneous function. So a function f in x and y is called a homogeneous function of some degree n if the following relationship is valid for all z, where z is any non-zero real number. So if you have any function f, it is called homogeneous of degree n if it satisfies this particular relationship that you are seeing on your screen. And here n, that is basically the exponent of z, and z is any non-zero real number. Here exponent n indicates the degree of that function. So if you have any function f and it is called homogeneous function only of some degree n if it satisfies this particular relationship, or you may say if you can transform your function into this particular relationship, then your function f will be called homogeneous function. So I'm going to explain that how we can identify a function to be homogeneous or not. So for instance, you have to keep in your mind the definition of homogeneous function, that any function that satisfy, or you may say that can be transformed into that particular relationship where z is any non-zero real number, then that particular function will be called homogeneous function. So let's see that how we can check a function is homogeneous or not. So here it is an example of homogeneous function. Consider we have a function f of xy, that is x square plus y square, and we have to check that it is homogeneous or not. So the very first step will be we have to multiply z with the variables appearing on both sides of the equation. That is, we have to multiply z with each variable appearing on both sides of the equation. And what is z? As in the last slide I have told you that z is any non-zero real number. So let's start. So the very first step to identify that a function is homogeneous or not is that you have to multiply that non-zero real number z on both sides of the equation, or you may say on both sides of the variable, So you have to multiply z with the variables involving on both sides of the equation. So let's start by multiplying with z. So after multiplying, you will get this form of the function. You can see that we have multiplied x by z, we have multiplied y by z, and the x square is also we have multiplied x by z, and the whole 2 power 2 is as it is, and same is the case for y. We have multiplied z with y, and the whole 2 power 2 is as it is. So now we are going to just solve it, or you may say just simplify it. After simplifying, we get z square x square here and z square y square here, and z square will be common in both of these terms. So after simplification and taking z square common, we will get this form of our function. And you can see that the terms involving inside the brackets are x square plus y square, and it is very clear that x square plus y square is our given function. You can see above the very first equation that x square plus y square is equal to f of xy. So you can replace this x square plus y square by f of xy. So this function can be written as f of zx zy, that is equal to z square, and x square plus y square is now replaced by f of xy. So this particular transformation of function is exactly the same as we have discussed in the definition of homogeneous function. If you are able to transform your function after doing these steps into this last form, it means that you have a homogeneous function. So we have a homogeneous function, that is f of xy is equal to x square plus y square, is a homogeneous function of degree 2, as the exponent of z determine the degree. So the exponent of z is 2 here, so we have our function of degree 2 here. So x square plus y square is a homogeneous function of degree 2. If we are not able to get f of xy here, then it is not a homogeneous function. As we are able, we have succeeded in transforming our function into that particular form. We have f of xy, that is the original function here. It means that we have a homogeneous function of degree 2. And you can also identify a function to be homogeneous or not by seeing the degree of each term. You can see it is also a or you may say a trick too, that if you have a function and the terms, the degree of each function is same, like the degree of x square is x is 2, the degree of y is 2, then there is a huge chance to a function to be homogeneous. So it is an example of a homogeneous function. Now let's see another example which is not homogeneous. So now we have to check this particular example. It is not a homogeneous function, I already told you, but we are going to check this too. So the very first step is to multiply z with each variable involving on both sides of the equation. So we have multiplied with z and we will get this. After simplification, or you may say the opening of the brackets, we will get z cube x cube plus z square y square. So z square will be common in both of these terms appearing on the right hand side. So after simplification and taking z square common, we will get this. Now you can see that after factoring out z square outside the brackets, or you may say after taking common z square, the terms inside the brackets are not exactly the same that we are given with in our function. Our function is x cube plus y square, but the term we are getting here inside the brackets are zx cube plus y square. It means we have extra z, so we can't say that these two functions, that is the given function and this function, you may say the terms involving inside the brackets are not same. It means we can't write into this function into this particular form, that f of zx zy is not equal to z square f of xy, as the terms involving here can't be replaced with the original function because of this extra z. So it fails the test of homogeneous function that we have discussed in the definition. So it means that this particular function, that is x cube plus y square, is not a homogeneous function. So this sums up the definition and examples of homogeneous function. Now we are able to talk about homogeneous differential equations. So here we have homogeneous differential equations. So what is the definition of homogeneous differential equation? If you have for any first order differential equation that can be represented in this form, provided that this function m and this function n, m and n are both the functions of x and y, should be homogeneous of same degree. So if you have a first order differential equation that can be represented in this form with conditions that m and n both should be homogeneous function of same degree, then this differential equation will be called homogeneous differential equation. So the for differential equation to be called homogeneous, the function involving in that differential equation written in that particular form should be homogeneous of same degree. In other words, you can define homogeneous differential equation in this way too. Like if you can express your differential equation in this form, like you have differential quotients appearing on the left hand side and you have the quotient of some functions appearing on the right hand side, with condition that the both functions f1 and f2 are homogeneous. So it is a condition again that if you can write the differential equation in this form, provided that, or you may say it is necessary, or with condition that the functions, both functions appearing on the right hand side should be homogeneous and the differential equation as a whole look like this, then this function will be called a differential equation, or you may say homogeneous differential equation. So both are the definition of homogeneous differential equation. So if you are able to transform your differential equation into this form with guarantees that the functions appearing on the right hand side here are homogeneous, then your differential equation will be called a homogeneous differential equation. And if you are sure that the functions appearing here are homogeneous differential equation, you can further transform your differential equation into this form. When f1 and f2 are homogeneous, you can write the differential equation into this form. Here g y over x, after verifying that the function you have a homogeneous function, you can transform your functions into this particular transformation of function. So this is basically homogeneous differential equation. So in order to identify homogeneous differential equation, you have to make that particular form, and you will have to be sure that the functions involving on your differential equation should be homogeneous of same degree. So let's talk about some example here. So here we have an example that is related to homogeneous differential equation. So here we have an example of homogeneous differential equation. So we are now going to solve it so that you people can get the idea that how we are going to solve a homogeneous differential equation. So the very first step will be, we have to identify that this particular differential equation is homogeneous or not. So for identification, you have to first transform this differential equation into that particular form that I have shown you in the last slides. We have our differential quotients should be on the one side and the functions of x, y should be on the other side. So we have to separate like the differential quotients and the functions of x and y. So we can write this particular equation in this form, that is xy dy equals, this minus sign will get positive after moving towards the right. So I'm going to move this particular term on the right hand side. So we will get x square plus y square and dx. So after moving dx on the left hand side and that particular product of x and y on the right hand side of the equation, we will get this dy over dx equals x square plus y square divided by xy. So you can see we have differential quotients on the one side and we have functions of xy on the other side. Now the other thing important is to check that the functions appearing on the right side of the equation are homogeneous or not. It is very clear, I'm not going to verify here as I have already shown the procedure for the verification of homogeneous function, or you may say for the identification of homogeneous function. If you multiply z with x here and y here, you will get z square x square here and z square y square here, and z square will be common, it will come outside and the remaining term will be the original function left. It means that this particular function is homogeneous. Same can be done for the functions appearing in the denominator. You multiply z with x and y, z square will be common, the other function left will be the original function. It means it is also homogeneous. So both of these functions are basically homogeneous functions. It means that we have a case of homogeneous differential equation. Now it is clear that we have a homogeneous differential equations. It means we are going to adopt the procedure that is required to solve homogeneous differential equation. So in case of homogeneous differential equation, we basically do a substitution. What we are going to substitute? We are going to substitute y over x equals to v. So this substitution will help us in reducing this homogeneous differential equation into separable differential equation, and the separable differential equations are comparatively easy to solve. So we are going to solve by separable differential method in the end. So first we have to substitute that y over x is equal to v, and we can write this particular equation into this form too, that is y is equal to xv. So I have just moved that x on the right side of the equation. Now we have to differentiate this particular equation with respect to x, as we have dx here. So we are going to differentiate this particular equation by with the help of with respect to x. So I'm going to differentiate here. So I'm going to differentiate that dy over dx, differentiating both sides. So if we differentiate this side, we have to apply the product rule for the derivatives. So applying product rule directly, x will be as it is. We have to derivate dv over dx. Now we have to write v as it is, and the derivative of x will with respect to x is 1, so I'm not going to write 1 here. So this is our final result. Now what we will do, we are going to place the value of dy by dx we have found here on here. So we are going to basically substitute this value of dy by dx, that is x dv over dx plus v here. So we are going to write that. So dy over dx by this equation is equal to x dv over dx plus v. So I'm going to write here in the place of dy by dx, that is x dv over dx plus v. So here we are also going to substitute the value of y. Over value of y is xv. So we are going to substitute value of y is equal to xv. So I'm going to write x square as it is, and on substituting the value of y, that is xv, and we have square here, so we will write as x square and v square. Now we will move ahead and we have to do the same for the denominators. We have to write x as it is, and on substituting the value of y, that is xv, we will get v here as there is already x, so it will become x square. Now again simplifying further, we can write this equation x dv over dx plus v equals, we can take x square common here, so taking x square common, we will get 1 plus v square divided by x square and v. So x square will be cancelled out, so we will be left with x dv over dx plus v equals 1 plus v square over v. So this is for instance our simplified equation, differential equation. Now we are going to solve ahead, and I am going to separate v's and x here. So moving on the next page. So I'm going to write this equation again so that you people don't get confused. So what we got, we have x, we have dv over dx, I'm writing the last equation we have formed, plus v, and we got 1 plus v square over v. So I am now moving this v on the right side of the equation, so this equation will become x dv over dx equals 1 plus v square over v, and that particular plus v will become negative v here. So solving through, you may say, LCM, we will get v here, 1 plus v square here, and that v after multiplying with that v will become v square, and we will get x dv over dx here. So this plus v square and minus v square will be cancelled out, and we are left with x dv over dx equals 1 over v. So you can see that this particular equation is basically is now a separable differential equation. We can separate v and x here. So this is basically the advantage of substitution, that whenever you have a homogeneous differential equation, by doing that particular substitution, you can transform your homogeneous differential equation into separable differential equation, and separable differential equations are comparatively some easier stuff to handle or some easier stuff to solve. So now we are going to separate v and x here. So we can write after this particular equation in this form, that is, we can write it as v dv and 1 over x dx. So this particular equation can be written as this. So this is a basically separable differential equation. You have separated the function y, so you have separated the variable v and the variable x with their corresponding differentials. Now we are going to integrate both sides. So we are going to integrate both sides. As we know that in separable differential equation, we basically do this stuff, we integrate both sides. So the integration of v with respect to v, that is, we will get v square over 2, and the integration of 1 over x is very clear. You already know that it is log of x, natural log of x, and you have to add some constant. So I am adding here log of c. You can add c, just for simplification purpose I am adding log of c, it is a constant. So now you know, we can use the property of logarithm here. We can write these logs as like that, v square over 2 as it is, and we can write with the help of property of log, that is log of xc. Now that particular 2 here can be moved towards the right side of the equation, so we will get v square is equal to 2 times of log xc, or you may write as cx. So again, using the property of logarithm, this 2 can be written like that, log of xc to power 2. Now what I have to do, that this is basically v square, so I am applying square root on both sides. So I am applying square root on both sides, so this will get cancelled out and we are left with v is equal to square root of positive negative log of xc. This is basically xc and divided by 2. So this is xc. So this will be the last step that I'm going to do now. So we know that we have substituted. In the last step, what we are going to do, as we already know, we have substituted in the very starting part of the question, that is y over x equals v. So I'm going to substitute that particular substitution back. So I'm going to replace that particular v by y over x here. So we can write it as y over x equals plus minus square root of log of x c and a to the power 2, and now I'm going to move that x over there, so it will be our final solution. Y is equal to x plus minus square root of log x c to power 2. So this is our solution. So in this way you are going to tackle the homogeneous differential equations. You have to first make sure that it is a case of homogeneous differential equation. Then you have to apply that substitution, that you have to substitute y over x equal to v, and after performing all the steps that I have shown you, you are able to transform your homogeneous differential equation into separable differential equation. And the separable differential equations are with the help of integration can be solved to that particular form, and you have to substitute the values back, and then you will have your final solution. So this ends up the today's lecture. So we will meet in next lecture with some new stuff regarding differential equation. So thank you so much for being here.